Okay, class, here we go. Let's try another video solution. I got a question here on 39, and of course this is supersonic flight. Maybe I'll review that real quick, but here's the question. It says a supersonic jet traveling at Mach 3 at an altitude of 20,000 meters is directly over a person's head at time equals to 0 as shown in the figure. Now, let me just kind of review. Let's say maybe the ground is here and the airplane is 20,000 feet, or for this matter, just any height. Maybe I'll put the airplane right there, let's say. Now, they call that time equals to 0 in the problem, and so I will ultimately. But if it's going really fast, 1 second later, it's maybe here. 2 seconds later, it's here, and so trying to get the same spacing. 3 seconds later, it's here, and then finally 4 seconds later, it's here. So it would travel, some distance. And since it's supersonic, this distance in 4 seconds, 1, 2, 3, 4, would be greater than the speed of the sound. So let's just say back here, 4 seconds before it got to here, we look at the waves coming off of it. Maybe I'll give it a distance about equal to one of these lines. And so maybe the sound wave would come here, and then the sound wave would come here, and the sound wave would come here, and then here. So it was here at some time, let's call it 0. 4 seconds later, it's here. And that 4 seconds later is how long it gets here. Now, I'm not saying this problem takes 4 seconds. I'm just trying to show you a very important picture here. And the idea in this drawing, and maybe I'll make some circles. 1 second. It was here. 2 seconds, 3 seconds. And I should probably just make this circle at 4 seconds. Because let's look at an instant in time when the airplane is here, okay? 4 seconds after 0. All right. So at 0, it was here. 4 seconds, it's later here, which means this wave is here. Now, a second later, it would have been here, and it would have made a wave that would have traveled 1 second, 2 seconds, and then 3 seconds. And my picture's probably not very good, but from this point forward would be 3 seconds, and so I should, be drawing a circle at around this point. This would be the sound waves produced there. Now, if you look at the sound produced here, it would be 2 seconds ago. So sound would have traveled 2 lines and a circle around here. And then the sound produced here would have been 1 second ago, so it would be about here. And now this one is just beginning to produce. But the point of this whole discussion is if you were to draw every infinite number of points that the plane had, you would have circles that the centers would be moving and they would be getting smaller. And all the circles would line up along this line. And that is, all the sound produced would be superimposed in the shape of a line. And so we like to draw then this shock wave. I think it's probably better to describe it as the wake of a boat. It's the same principle. The waves are water waves instead of sound waves, but you have this wake, and many people have seen a wake, and so they can visualize this a little better than they can a shock wave. But it's the same thing. In fact, a shock wave's three-dimensional, so it's more of a cone in 3 dimensions that comes out, and that can't really be drawn well on this flat piece of paper. And then water waves, of course, are just 2-dimensional on the surface, so if you can kind of imagine this shock or water wave, this wake, and then you rotate it to make a cone, that would be this shock wave. But here's the key to the problem then, is to realize then that if you look back at it, this distance right here would be the velocity of the object. Maybe I should have looked what symbols. I think your author uses a velocity of s, because we've been using velocity s for the source of our sound, multiplied by time. And the sound wave would have been, if you draw it perpendicular, and my drawing's not very good here, but I'm trying to draw a perpendicular so that this, is the direct line as this shock wave is coming out, and then there's this angle theta. Whereas this would have been the velocity of the wave and multiplied by its time. And of course, velocity of the wave, we've been just using a v. And so the point is, if I go sine theta here, I have the opposite over the hypotenuse. So the opposite is Vt and Vst. The t's cancel. And then this tells us something about this angle. And so what we call the shock angle here is then related to this relationship between the velocity of the waves and the velocity of the source. And in fact, the velocity of the source compared to the velocity of the wave is what we call its Mach number. And so this would be 1 over its Mach number. So simply put, for this problem then, since I said it was Mach 3, I could go sine theta equals 1 over 3. And of course, now I can grab my calculator. All right, let me check what mode I'm in. Looks like I'm in degrees. So let me go to radians. We're talking about a real number here. And so 1 divided by 3. Now let me do the inverse sine of that number. And so, well, I think I would have liked that better in degrees. Well, so I'll do both. So in radians, it's 0.3398. And we're taking a ratio, so whether it was in radians or not didn't matter. Let's do this in degrees. Let's switch my mode back over to degrees, and let's do this again. Inverse sine of 1/3. And so we're looking at about 19.5 degrees for the angle of our shock wave. Okay, so that's what I know right already about Mach 3. Okay, shown in the figure. A says, at what time will the person encounter the shock wave? And then B, where will the plane be when the boom is finally heard? Okay. Well, the shock wave, if you will, let's see if I can kind of imagine this wave coming out here. This one is going to be somewhere along those lines. But I probably should have drawn, maybe I'll draw a new one here, a tangent angle. And let's do this. And so instead of drawing ... the one that we derived for the Mach wave, let me draw the one that's 19.5. Let me evolve the one that goes straight down, because we know this is 20,000 feet or 20,000 meters. So if I call this, maybe just for a moment, h, and maybe this distance x, then the tangent of theta is h over x. And so x would be h over the tangent of theta. And so h is the 20,000. Now I need to come back and read the problem. Was it 20,000 feet or 20,000? Oh, 20,000 meters. Okay, good. Meters. And then this is the tangent of 19.5 degrees. Okay, so grabbing my calculator, I'll go 20, 1, 2, 3,000, and divide it by the tangent of 19.5, and so the plane would have gone 56,000, let me just round it to 56,500 meters, or maybe I should just say 56.5 kilometers. So there is the x distance. And I believe that was question B, how far? Yeah, where is the plane? That's the one that kind of stuck in my mind as being a little bit easier. Let me go back then to A, so maybe I should have labeled that B, and I'll come over here and say, okay, well, let's look at then A. A says, at what time will the person encounter the shock wave? Okay. So maybe the thing to do is to look at the speed of the plane. We know distance equals to velocity of the source times time. We just calculated the distance it's going to move is 56,500 meters. We know the velocity is Mach 3, so that means 3 times the speed of sound. And they give us a little bit on the small side, I guess, because the upper atmosphere is kind of cold. So we'll go 335 and then solve for time. All right. So I still got that number in. So let me divide that by 3 and then also divide it by 335. And I get a time of 56.2 seconds. So not quite a minute, but pretty close. All right. Hope that helps.